Alrighty, so welcome to obtuse angles and exact values. Now, we've been doing trigonometry and it's always involved right angle triangles, okay? And we've made a big emphasis on it being for right angle triangles. However, there are some specific applications when trigonometry is related to a circle, okay? Now, you might be saying to yourself, well, how can this be the case? How can something to do with right angle triangles be related to a circle? Well, that's what we're going to spend this lesson exploring, okay? So, this object, what I've got here, is called the unit circle, okay? And we're going to explore this in more depth at a later date. But today we're going to be mainly focusing on two of the quadrants, okay? In fact, it's the top half of this circle we're going to be focusing on. But I thought I would introduce the whole thing to begin with, okay? Now, the reason this is called the unit circle is because it is a circle that has exact length, or exact radius, I should say, of 1. So wherever I draw a radius for this circle, okay, it's going to have a radius equal to 1, okay? So it doesn't matter where I draw it, the radius is always equal to 1. And we know that with circles, we know that circle always has a radius of 1, okay? Regardless of whereabouts you draw it, the radius is always equal to 1. Can I get rid of this without deleting everything? Oh my god, I'm good. All right. So yeah, we've got this radius of 1, okay? Now, what we need to do is we need to think of this as maybe a circle that's drawn on a Cartesian plane, okay? And each of the points, or each of the parts along this circle here, okay, can be represented as a point, okay? It's like a point on a Cartesian plane. So when we've previously done Cartesian planes, and when we've done points on a Cartesian plane, typically we tend to draw straight lines, okay? In this case, we've actually gotten a circle, and we can do some things with this circle, with the points on this circle. So I'm going to pick a specific point. I'm going to pick, say, this point here. Okay? It's just a random point I've picked. Okay? And I'm going to draw the radius, okay, for this particular point. Okay? Now, we know that the length of this radius is equal to 1. Okay, we're not going to argue that, okay, because it is a circle, and so from the center to the edge, no matter what edge I've got it towards, it's going to be equal to 1. Now we need to define a couple of things, okay? This point, the position of this point, I'm going to use a general term, okay? So this point I'm going to call P, and it's going to be made up of an X component and a Y component. Now I don't know what these X or Y components are, okay? It could be, like a half and a half, okay? Because a half and a half, or maybe not a half and a half, but it could be like, two, like they're two numbers, that are going to make, this circle exist, okay? And there's a few ways that we can actually come up with those numbers, and we're going to talk about those very shortly. Excuse me. Now, another thing we're going to define is the angle that we're going to be using, the angle we're going to use to calculate some values in this, okay? And so the angle we're going to use is this one in here. So we're going to call this the angle theta. So we've got a point, which we've called xy, so we don't know what those values are. We've got an angle theta. Again, we don't know what this angle theta corresponds to. If we knew what the point was, we could work out what the theta is, but remember, this is in general form, okay? Because we're basically making a formula that represents everything. But the only thing that we do know for certain is that the radius of this, or the hypotenuse of a right angle triangle, if I was to draw it in like this, see, I've got this right angle triangle here. The hypotenuse of this right angle triangle is equal to 1, okay? Now, the reason why I want this is because we can define our trigonometric ratios based off the triangle that I've drawn here, okay? But we need to take this one step further, okay? We need to work out, well, what is this side equal to? And what is this side equal to? What are these sides equal to? And we're going to leave it in general terms, okay? So that is, we're going to leave them as just pronumerals, because we don't know what these are. They're going to change based on how far around this angle is. Like, it could be around here, okay, like that, and it's going to change because it's gone further around. So, well, what are these values equal to? Well, this side along here, so this one along here, is just however tall the line is on the y-axis, okay? So it's basically just this length here, whatever this length is along my y-axis. So what we're going to do is we're going to call this value y, okay? Which is the same as this value y here. So if I knew, just as an example, if this value for y was a half, okay, then this length down here would be equal to a half, okay? But again, we're generalizing this. We don't know what it's actually equal to. We're making some formulas up. Now, you could probably guess what the other side's going to be equal to, but this value along here, okay, is representing how far along the x-axis we are. So we're going to call it the x. And again, that x is the same as this one here, the x value, which we don't know, okay? So again, if this x value was equal to, say, you know, like, it could be something less than 1, so let's say it was like 0.2, then this x down here would be equal to 0.2 as well. Again, we don't know what these values are, we're just generalizing it. Okay, so now you're probably asking yourself, you might be a little bit confused, like, why on earth are we doing this, okay? Well, the reason we're doing this is because we can now define the trigonometric ratios, okay, as values on this particular triangle, okay? So what I'm going to do is I'm just going to transpose this triangle, okay, down here, and we're going to redraw it, okay? So what's this triangle's dimensions? Excuse me. Well, this triangle's dimensions, okay, we know that this length here is 1. We know it's a right angle. Okay, we know that this angle in here is theta. Okay, and then looking back up here, we know that this length along here is y, and this length along here is x. And what we're going to do with this triangle is we're actually going to rewrite our sine, cosine, and tan ratios from this triangle here, okay? So sine of theta, let's work it out from this triangle. Here's my angle down here. So sine of theta, okay, well, what's sine? Again, so let's think of SOHCAHTOA. Put it up here, SOHCAHTOA. Sine is opposite on hypotenuse. So my opposite value is my y. My hypotenuse is 1. So I can rewrite sine as y over 1. And what is y divided by 1 equal to? Well, that value is just equal to y. Okay, so basically what this is saying is, if I've got a triangle that's hypotenuse is 1, whatever the opposite side is equal to is exactly what sine is equal to. So sine of my angle is exactly equal to whatever that length is. And this is really useful for us to know when it comes to the exact values, which we're going to look at in a moment, okay? Now let's do the same thing for cosine. So cos theta is equal to, okay, well, cosine, okay, think about cosine, it is adjacent over hypotenuse. So this one's going to be x over 1, which of course is just equal to x, okay? Well, that's pretty cool. Okay, so that means whatever this length here is in my triangle, and that's with my hypotenuse equal to 1, of course, cos of that angle is just going to be equal to whatever this is, whatever this length is down here. And again, only when the hypotenuse is 1. Okay, finally, we've got the tangent one. So tan theta is equal to, okay, so tan is opposite over adjacent. Okay, well, that's equal to y over x, okay? But we can rewrite this because up here we just decided, well, sine theta was equal to y. Okay, we just wrote that up here. So where I see my y up here, I can actually replace it with sine theta. And the same thing goes for the cosine and x as well. We worked out that, well, cosine is equal to whatever x is, and here's an x down here. So this is basically just cos theta, okay? So what this bit's saying is that, well, tan theta is equal to sine theta over cos theta. So if I know what sine theta is, and I know what cos theta is, well, I can work out what tan theta is really quickly. Okay, and so this brings us to our three ratios. Sine theta is equal to y, so whatever our y value is, and we'll have a look at some examples of these as well. I'm not just going to be like, here it is, now do some work, of course. Cos theta is equal to x, and tan theta is equal to sine theta over cos theta, because we worked out that it was, well, y over x. And if y is equal to sine and x is equal to cos, then it must be equal to sine over cos. Okay? So this is basically what these ratios can be equal to. And this only works in a unit circle. Okay? So these values only work in the unit circle. Now, the values can change, will change, I should say, depending on what your hypotenuse is. So if your hypotenuse is 3 or 5 or 7.5, like the values of your sine theta and cos theta are going to change. So right up here, only works for the unit circle. Okay? And we'll leave it at that for now, because as I don't really want to get into it, because there is cases where obviously you can manipulate this, and if you've done similar triangles, you'll be able to see the connection. But for now, we're just going to say this only works for the unit circle, okay? Excuse me. So this means that we should be able to work out some values based on our unit circle. So we can go back up here and look at our unit circle. And if we know some y's and x values, or we know an angle, we can actually work out what these values are equal to, okay? And it's actually really quite cool. Well, I think anyway. You might be of a different thought in that case. But the main application of this is being able to look at other angles in our or other angles other than from 0 to 90 degrees. Because when we've done trigonometry, it's always been in right angle triangles, and the right angle triangles that we've been producing have always been triangles that are between 0 and 90 degrees. Because if one angle is 90 degrees, then there's no possible way for the other two angles to be bigger than 90 degrees, because otherwise we wouldn't have a right angle triangle. Okay. So what do we mean exactly then by obtuse angles? Like, why has obtuse angles come up all of a sudden? Okay. Well, one of the cases is obviously for non-right angle triangles. Okay. And these trig ratios, some of these trig ratios, there's different formulas for them, but they do come up with non-right angle triangles. But the thing is that we might be asked to solve an equation, or an equation that has one of these trigonometric ratios in them. And that's what we're going to be looking at. So what I'm going to do is I'm going to take just the top half of my unit circle. Okay? So let's go. That's not a circle. Really bad shape. Oh, that's even worse. Is there a circle showing shape on here? Oh, excuse me. It's not letting me draw the top half, so I'll tell you what I'm going to do. I'm going to cheat. Copy this. Oh, it's not letting me copy that. Okay, I'm just going to have to freehand it then. So something like this. Okay. So here's our circle here, or something of a circle. And this is just our top circle, okay? Now, what we're going to do is we're going to write in some values. So this is 1 long here, this is 1 up here, and this is -1 up here. Okay, because the radius is one unit long. Okay, now we're going to define some quadrants. Now we call this quadrant over here, so this is the top right quadrant. We call this the first quadrant. Okay, and then we've got the second quadrant over on this side. And in the next lesson, we're going to look at the third and fourth quadrant as well, but we're mainly going to focus on this first and second. Okay? Now, conveniently, every single radius I draw on this is going to be equal to 1. Okay, so let's draw a line like this. Okay, and we're going to put 40 degrees in here. Okay, and I'm going to make a right angle triangle based on that corner. Okay. Now we know that this length here is 1, and from above, remember, we drew this triangle already. The opposite side is y, the adjacent side is x, and we're going to call them those. Call this side y, call this bottom bit x. Okay, and what we can do is we can actually find what these values are. So, how do we do it? Well, glad you asked. Just trigonometry, okay, with our y value and our x value. So in this case, remember, these formulas are just here. Sine theta is just equal to whatever y is, okay? So if I know what sine theta is, okay, if I know what theta is, I can work out what y is very, very quickly. So in this case, y is just equal to sine of my angle. And my angle in this case is 40 degrees, okay? So all I've done is I said that this opposite side, and this all is due to the fact that this hypotenuse is equal to 1. So this wouldn't work if the hypotenuse wasn't equal to 1. But because the hypotenuse is equal to 1, okay, we can just say that, well, our value for y is just sine 40 degrees, okay? So put that into your calculator, sine 40, and there you go, it's 0.6428, okay? And we'll do 4 decimal places. So 0.6428, okay? And again, we can find what our x value is as well. Okay, so our x value is just cos of 40 degrees, okay? So cos of 40 degrees, and we put this into our calculator, and we should get 0.7660, okay? And so that's all it is. Like, that's how you find the y and the x value from this diagram, okay? So why is this actually useful? Well, as we were saying before, this has something to do with obtuse angles, okay? And I'm going to do this next bit in green just to show you the difference. Now, let's just pose the question, okay? Well, I want you to tell me what sine of, say, let's say 140 degrees is, okay? 140, no, we'll go, yeah, 140. And what is cos of 140 degrees, okay? What are these things equal to? Okay. Now, again, we've only dealt with trigonometry in between 0 and 90 degrees. So can we do anything that's bigger than 90 degrees? Okay. Well, let's think about where this would be situated in our diagram, okay? So we've got the 40 degrees, it's from here to here, okay? So we're going anti-clockwise around from where the x is equal to 1. So basically, we're starting out here, so my direction is out this way, and we're traveling in an anti-clockwise direction, okay? So I'm looking out this way, so I'm looking out this way, and I'm traveling in an anti-clockwise direction around that way, okay? And so I need to travel 140 degrees. So, well, how far around is that? Well, from here to here is 90 degrees. And so if I travel an extra 50 degrees, okay, 50 degrees around here, I should come up at this value here, which is 140 degrees, because it's the 90 plus the 50. Okay, well, that's curious. So why is that helpful? Okay, why do we care about knowing how far around we're going to go? Well, maybe you've picked up on it, but if I was to actually create a triangle coming back this way, what's my angle in here? And what's my angle up here equal to? I'm going to zoom in. What's my angle in here equal to? So that's this angle in here, okay? So I've got 90 degrees here, plus the 50 along here, which makes 150 in total, 140 in total. So what's left over? Okay. Well, if I was going all the way around, I'd have to make 180. So 180 take away 140 should give me what's left over here. Okay. Well, what's that equal to? Hopefully you saw it. It's 40 degrees, okay? Well, that's really cool because what we've essentially got is we've got the exact same triangle as the red triangle, okay? There's only one subtle difference though. So it's the exact same triangle, except it's been flipped. It's been flipped over. Okay. So let's have a think about the sides. Think about what the length of the sides are. The length of my radius, my green radius, well, it's still equal to 1. Excuse me. Okay, it's still equal to 1 because it's still going from the center out to the edge, so that's still 1 unit of length long. What's my height going to be equal to? So how tall is this bit going to be equal to? Well, it's the same as this height over here. They're both going in that positive upwards direction. So that's just equal to y. But for our bottom length, okay, we're not going from the center to the right this time. We're actually going from the center to the left. Which direction are we heading in? Okay. The red line is heading in the positive direction, so it's positive x. The green line, which direction was it heading? It was heading in the negative direction, so we need to put negative x down there. Okay. Now that might seem a little bit odd to put a negative there, but basically all this means is that when we go to use the value for x, whenever we're using an x value for this second quadrant, so as soon as I've got an angle that's in the second quadrant, we're looking at a negative value of whatever x is, okay? So, 2 key points. So, let's write these in. For 140 degrees, it is the same as the triangle with what? Or what angle? Okay, for 140 degrees, it is the same as triangle with what angle? Okay. With a 40-degree angle. Well, there should be an A in there. With a 40-degree angle. Okay. But this shouldn't be a, that should be a, it should be a comma, and not a capital B. Ugh, let's just again. But the x values are going to be negative. So this basically means anything that uses, I'm going to put uses in inverted brackets, commas, uses the x is going to be a negative answer, okay? And I'll show you exactly what I mean by this, okay? So let's go back and have a look. We're doing sine of 140 and cos of 140, okay? So we said that sine 40 degrees was equal to 0.6248. So sine of 140 degrees. Now remember, sine uses the y. So because sine uses the y, it shouldn't change. It should just be 0.6248. So let's have a look. Sine of 140 degrees. Look at that. 0.6428. Did I write these numbers in the wrong way? No, I didn't. I just wrote it down here wrong. 6428. Now let's look at the cosine. Well, cosine of 40 degrees was 0.7660. Now the cosine rule involves an x. So this means that our answer should be the same. It should be the same because it's the same triangle, but negative. So what does this mean for you guys? So what this means for you guys is the following. If you know what the sine or the cosine is for one of the values, so for an acute angle, so between 0 and 90 degrees, then you can work out what the obtuse angle is, okay, by using the rules that we've just stated above, okay? So as long as they create the same triangle, so the creation of the triangle is that theta is equal to 180 degrees minus the other angle, which we'll call, say, alpha, where alpha is the obtuse. Okay. So my little angle has to be equal to 180 degrees minus the bigger angle, okay? So from above, the example from above, theta would be equal to 40 degrees because that was my small angle. Alpha would be equal to 140 degrees. So does 40 degrees equal 180 minus 140? Okay. Well, yes, it does. And so that's why this one works. Okay, so it's the same. Now, if we tried, say, at 40 degrees and 130 as our obtuse angle, then we'd have something that's different. But ultimately, at the end of the day, you have your calculator that's going to do this. This is the theory behind why this all works, and this is quite a long video too. But essentially, the point is that you're going to be able to work out the sine or cosine of an obtuse angle very, very quickly. Okay? Now, what we're going to do is we're actually only going to focus on the obtuse angles today. We're going to look at exact values in another lesson. Now, one of the little, we've essentially got three rules, okay? So this is basically called the supplementary rules, okay? Because the angles make supplementary angles, okay? So it's 180 degrees. So essentially, okay, the three rules are if you have cos of 180 degrees minus the angle being equal, well, it's essentially going to be equal to negative cos of the angle itself. So e.g., cos of 180 minus 35 is going to be equal to negative cos of 35. Or in other words, cos of 180 degrees, cos of 180 minus 35 is, what's that? 145 is going to be equal to minus cos of 35. Okay. The second rule is for the sine. So sine of 180 degrees minus theta is going to just be equal to sine of whatever that angle was. Okay. So e.g., so we'll do the same one. Not cos, we're going to do sine of 180 minus 35 should be just equal to sine 35. Okay, so if you know what sine of 35 is. So in other words, sine of 145 degrees is just going to be equal to sine of 35 degrees. Okay. Now the last rule is for about tans. So tans follow the same rule. 180 degrees minus 35. I've done this around the wrong way. Sorry. 180 minus theta, and it's equal to negative tan theta. Okay. So e.g., tan of 180 degrees minus, say, 35 should be equal to minus tan of 35. And in other words, tan of 145 should be equal to negative tan of 35. Okay. So that's a lot of information to take in, and I understand that's the case as well. We're going to leave it at this for today, and we're going to split this lesson up into two. Okay, I was going to try and get through both, but I think for you guys for now, we're going to leave this as is, and I want you guys just practicing the obtuse angle. Okay, So supplementary, add up to 180, and then I want you to have a go at doing some of this stuff. So please ask questions with this stuff too, because I know this one's going to be a bit trickier, and I think I'm going to lose a lot of you guys throughout this video. But the work itself is not too tricky. Okay, you're basically looking for the complement of most of the values. Okay, so we'll leave it at that, and I will catch you guys in the next one.